Hello, today I'm going to talk about Cauchy function for solving ordinary differential equations and Butcher tables. So at first we define the Cauchy function as a function that depends on time and a vector that depends on time too. So when we apply a function f, so this will be the Cauchy function, it will differentiate it, which means for each part of the vector it will derive it over time. So if we take this linear equation, this differential linear equation, we can translate it into um, a matricial system because we have two variables, y and y prime, so the derivative over t, that satisfies two different equations. But what are those equations? So we call y1 to be equal to y, y2 to be equal to the derivative of y over t, and y3 being the second derivative over t. So we can replace our first equation, and this will parameter a system. So this will be our first equation, and the other equation is just the definition of y, because if you differentiate y1, which is also y, you get y2. So when you differentiate y, you've got a differentiate of y over t that is also the previous vector. So the top here equals the bottom here, while this can be expressed using this one because we get y2, y3 that is here, that can be expressed linearly as a function of y2, y1, and constants. Yes, so we just gather all that info. So we've got our two elements of our function, and then we write the differentiate that is y2. So the second element of the vector comes as the first element of the vector. As for the second differentiation, you can express it using the formula we've given. So if you use MATLAB as an example, with 1 and 2 being the two vectors of y, so the two parts of v, so if v1 and all the other parts are time, you can do a slicing. So you get y2 here, that is affected to the first variable. So in MATLAB, this means a vector. So this thingy here means the vector. This will separate all the coordinates. So this is the first coordinate, and this is the second coordinate. The first coordinate comes as the first vector, and we do a slicing over all the time variable, because when we do it in MATLAB, our vector has two dimensions in terms of y and y prime, but it also has dimensions of time, because we have all our values, so t at 0, t at 1 second, t at 2 seconds, t at 3 seconds. So we do a slicing over all the time variables. For the second one, we just plug in the same thing based off the equation. And we also do a slicing. So, yeah, also, as I mentioned here, nothing constrains it to be a function of constants, because you can also have functions that depends of time in different problems. So you can have, instead of c, you can have cos t times y1. That can be interesting to see. So in general, the general form, it's a function that, as you associate a vector y and t, and that has the same dimension based off t and y, obviously, and that does the differentiation. So so we're going to talk about the first method. So the progressive Euler is the most easy. It is the easiest one. It's the one you usually learn at first. So you get the value over n plus 1 in terms of time. So all the vector, all the parts, so the first value are y and its derivative. So it's this represents a vector at the value n plus 1. So so the time over the new one that we will iterate based off the previous one plus h time f of tn and yn plus O of h. O of h means the big O of Landau. You have to see the Taylor theorem to get this. So you usually find a formula like this. We will talk about it later on a later video, but I'm going to talk about it later. So we've got our system that will approximate derivative with a certain error, that is O. With this method, we can have a basic understanding of the function. It's very cool because you directly have the expression of yn plus 1 as a function of yn, but there are other methods that aren't that aren't that aren't explicit, because the progressive Euler is explicit, meaning that you have n plus the vector at n plus 1 being directly a function of n, but sometimes it can be implicit, meaning that you have n plus 1 on this part and n plus 1 on this part, and you can't factorize easily. So those methods are called implicit. So I'm going to deal only with explicit methods because they are the easiest one. And when you want to use an implicit method, you have to use explicit as well, or very specific boundary conditions. So Runge-Kutta 4, I pick 4, but it can be any number, any integer. So we build k1 being a slicing over all the variables of the vector at the time n, being the function of tn, so the time n, and the vector y at the time n. So we build another k2 being a function of tn plus h over 2, and on the other part, so y at the time n plus 1/2 of k1. And we will keep building those variable k's, so k1, k2, k3, and so on. And then we will sum them using this formula here. So 1k1 plus 2k2, so one here and one here, plus 2k3 plus k4. And this formula will give an approximation of the derivative, plus O of h to a certain power. What could it be? What could it be? Usually, when you say you Runge-Kutta something, it means the order, and it can be demonstrated easily. And we're not going to do this demonstration, but basically you build sub-variables that are function of functions, and then you sum them finally. I don't know exactly the demonstration for this, but I know it can be demonstrated easily. So the Butcher table is a tool for designing methods. So we will use methods that have only one h, so h being the discretization step, so like the difference between your value t0 and t1. So So it's just the difference. If you have if you start at t equal 1 and you want to end at tf equal 1 second, no, t0 equal 0 second and tf equal 1 second. If you have 10 value, then h will be 100 millisecond. Yeah, 100 millisecond. So we build a system that will have a function phi and a bunch of vector and matrices. So the vector A, the matrix B, and the vector C. So we will build the same thing as yn plus 1 equal to yn plus h times phi. So phi, you can notice that it strangely represents this. So this part here. Phi being the sum over ci of ky, and k1 being the function like this. So you have to define properly y, a, and b, with b being a vector and I and c being two vectors. And then you can build a method with constant step. So this butcher table with the example of Runge-Kutta, you get something like that. So you can, if you replace it, you'll get something like this. Now various results for COMSI people. So if AI, so all the values equals the sum over I, so if you sum each line, you get order 0. So here we get 0 plus 0 plus 0 plus 0 equals 0, 1 half plus 0 plus 0 plus 0 equal 1 half, 1 half equal 0 plus 0 plus 1 half plus 1 half, 1 half equals 0 plus 1 half plus 0 plus 0, 1 equals 0 plus 0 plus 1 plus 0, so it's order 0 at least. Order 1 if it's order 0, and the sum of I is equal to 1. So we can quickly verify that the sum of this is equal to 1. And if order 2, if it's order 1 and the sum of AI CI is equal to 1 half, so AICI, so it's 0 times this, this times this, this times this times this. Yeah, it should work because we are in the Runge-Kutta 4. So yeah, that's a result that can be interesting. About the initial conditions, so I didn't clearly detail it because I want to talk about it in a later video. Usually we will work with conditions at t equals 0. So we have our vector at t equals 0. Oh, that's the mistake. Here our variables are usually the position, so not the derivative, and the derivative here. So because usually when you have a system, you know its position and its velocity. Usually you take a 0 velocity. So that's a mistake here. So when you parameterize the value that the vector y takes at 0, you have unicity, and that is guaranteed for linear systems by the theorem of Cauchy-Lipschitz, as we call it in France. And I have heard that it's called Picard-Lindelhof for English speakers. So as a conclusion, I say thanks for watching, but also I'm going to do another video that I've ready and I'm going to record right after, that is on a slightly same subject but not really, that talks about this, about partial order equations. So if you have any question about this, feel free to ask them in the comments. And bye.